This is the midterm exam for CSE 546, Introduction to Machine Learning. It's Jordan Richardson. I'm in section 51, which is remote. For this problem, we had to create a data set, 20 samples. SVM should be able to correctly classify all with no reg or mess up with reg. The way I did this was putting in outliers. So I actually verified this example in VS Code, just in Python, just to see with regularization or without. And I was able to verify that it did make a mistake. So basically it'll put a decision line through here, and if it doesn't get it perfect, then these would be misclassified. So if it, for example, did like a line like this, then it would split blue with red and red with blue. But both of these can be good for you, considering on the scenario. So misclassifications, or at least just this one, could be better because there are larger margins between the classes, so it might perform better on new data. When none are misclassified and gets all of them right, that may be better because you may not have a lot of data. You may not be able to tolerate classifications. You may need 100% accuracy. There's a couple of reasons why that could be better. It's the same thing for problem 2, except we are using a decision tree classifier, and change was if depth is less than 3 or depth is greater than 3, then it should succeed. I also did the same thing with an outlier on this one. And I was able to run this, and it was able to basically box off all the reds kind of into their own box, as well as the blue, depending on the depth. And I was not able to get it with 3. So the way I kind of did this by hand to show my work, started at the x equals 5. I split the data into 10 samples on each side. That was just my initial split. For the left branch, I decided to split at 5. I could have maybe split it at 6, but I split at 5, and I predicted that blues would be up here. So that means that these 3 would be misclassified at that depth because we haven't split them away from these blues yet. And then we did the split at y equals 4 on this side. That would split the blues up top and the reds down below. And this one would also be misclassified because of that. For problem 3, we basically just had to define the best model for each of these 2 data sets. For this one, I said the best would be random forest or decision, but I believe random forest is the better choice because of non-linear decision boundaries are really probably the best for this problem, considering how close the data can be together. There's blue right in the middle of the orange. Decision tree could probably still do this, but random forest would definitely be the better model. For this data set, I think decision tree is the best without a doubt. You can easily box off all these oranges with decision boundaries, and then the rest would all be blue. Other models could probably do this, but decision tree is the most simple and makes the best sense. Problem 4, 3 ways to reduce overfitting. I did cross-validation. It's a way of splitting your data into multiple subsets. It allows it to train on different parts and validate on the remaining, and then that gets repeated multiple times, which basically prevents it from specializing on one part of the data. You use this when you have a limited amount of data or during the model training phase, so you can evaluate how parameters are working. It allows the model to be, it reduces overfitting by preventing it from specializing on one subset. Regularization is another method. It adds a penalty to the loss function, which decurs complex models. Most common are L2, L1, or ridge and lasso. They both work a little bit differently, but they both work by adding a penalty to the weights. You use it when the model has too many features or a lot of noise and you don't want to fit that into your model. It's also commonly used with linear ones. It reduces overfitting by discouraging the model from building a large coefficient. It also shrinks less important features in L1 all the way to 0, which means only important ones will actually get used, helping reduce overfitting. Pruning is another method I've used a lot, mainly for work, but it's used in decision trees, and it removes sections of the tree that do not basically contribute to the model or its predictive power. There's two methods. You can pre-prune by defining a depth that the tree can't grow beyond, or a minimum number of samples. Post-pruning is after the full tree is created, going back and pruning branches that aren't adding to the model. You would use this when using decision trees or something like the random forest. If the decision tree grows too deep, it may learn specific subsets of the data. It reduces overfitting by simplifying the decision boundaries created by the tree, making it less likely to memorize exact parts of the data, which allows it to generalize better. Problem 5, we ran 2 models using the digits data set, which is pixelated handwritten numbers. For gradient boosted regression tree, I was able to have it generalize very well. I had 96.88% validation, 100% training, and 96.4% on test. So the model was not overfitting in any manner at this point. They're within 5% of each other, training and test. I did have quite a few misclassified samples, I guess you could say. Most of them range around 1 to 2 in the classes. And the reason some of these might be easier to classify than others, or why you might be seeing 1 and 1, but more in another, is because of what the data is. Just how people write numbers differently every day, they can be mistaken for other numbers, which is probably what the model's experiencing. For an example, I took this from a later part of this problem, but this is supposed to be a 3 that the model will read from. This is the pixelated image, but when I first saw this, I actually thought it looked like a 7. So you can see how the model might be making mistakes on this data. This is the heat map for all the pixels. So this shows where all the pixels in all of these images are hitting. So you can gauge that this pixel specifically is very important, and these pixels are not important. And these are technically the features. Next we did support vector machines, or SVM. I was able to get it to generalize very well. I got 99.184 on validation. Training was 100 and test was 99.1 repeating. So it generalized very well to the new data. I actually had 4 classes that misclassified, even 1 sample. So there weren't many misclassified. I then had to compare the predict proba of each. But I had such high accuracy that when I ran this, I actually got 0 samples back. So I had to basically bring these thresholds closer together so that way samples would come through. But I still got 1 in group 1. 1 in group 1, 1 in group 2, and none in group 3. So these are samples from group 1. So this was hard to classify by GBRT, but easy to classify by SVM, and this was the opposite. And then these are the misclassified samples for these. So you can see that really both the models were doing very well. That is it for my document. Now I'll go to my code. Hello, my name is Jordan. and I'm going to be going over my code now. So this is first for GBRT. So we load the data in, we set up the grid search. I actually removed all the extra parameters just so I can kind of show you that my code runs. Then you perform the grid search. It will find the best parameters. I tested quite a large range before I was able to find that. So this would print the best parameters, which was how I was able to set that. Then once we have that, it evaluates on test and train. So it generalized very well. We identify the misclassified samples. So we had quite a few for GBRT. So I actually kind of wanted to see how it was misclassifying stuff. So this is a confusion matrix. It shows basically how things are being mapped. And then this is the heat map that we made. This shows the feature importances for the digits data set. So it's pixelated data, so it might be hitting any of these points. This one's probably very important because you can see it's way up here. But these are probably not because they're very dark. So then I had to get to predict proba. I saved that over here, and then I go into SVM. So for SVM, I basically have the same setup. I load digits, training and testing. I pull back this proba from GBRT, and then I set up all my parameters basically. I execute the grid search. This was something actually that I hadn't seen before. I don't know if this is just something that's built into PYMB, but I thought that was cool. So we get the best parameters. This helps me find the best. It actually did very well. So I actually never ever changed my parameters from the first time because it did great. I did test a couple more, but it did great, and this was the best I got right off the bat. This is the training and testing. Misclassified only had 4 classes that had incorrect samples: 9, 8, 5, and 3. So I get the predict proba for that. And I analyze the scatter plots for 0, 3, and 7 classes. But my accuracy was very high, so not a lot of them are far off. There's a few that I guess could maybe be considered off, but you could see that it did very well on all of these. So then we identify groups based on those classes and the predict proba from each of them, and we append them to the group depending on these thresholds. And then we display the samples from each group along with their true label, because I was looking at images and getting confused. So I set it to display 5, but I actually only got 1 image in group 1 and group 2, and in 3 I was not able to get one regardless of what I did with the threshold. So explaining some commonalities between these, basically they're handwritten numbers, and it uses these pixels and where they are to try to classify it as a specific number. Both of these are 3, but as you can see, some of them can be snaking for other numbers, as this kind of looks similar to a 7. That's it, and thank you.